Oh my goodness, what do we have going on now? Our next question is 100% going to come back, and this is part of what drove this theory absolutely nutso. Let's dive in. The statement is, with the inclusion of the radiation reaction force, Newton's second law for a charged particle becomes A equal tau A dot plus F over m. Okay, that's the sum of forces, F equal ma, where F is the external force acting on the particle. A. In contrast to the case of the uncharged particle, where A is just F over m, acceleration, like position and velocity, must now be a continuous function of time, even if the force changes abruptly. Prove that A is continuous at any time t by integrating the equation of motion above from t minus epsilon to t plus epsilon and taking a limit as epsilon goes to 0. B. A particle is subject to a constant force F beginning at time t equals 0 and lasting until time capital T. Find the most general solution A of t so that the equation of motion in each of the three periods, where we have t less than 0, time between 0 and the capital T, and for time greater than capital T. Okay, those three regions will come back again, I promise you. C. Impose the continuity condition A at t equals 0 and t equal big T. Show that you can either eliminate the runaway region, 3, or avoid the pre-acceleration region, 1, but not both. Here's where we get tricky. Part D. If you choose to eliminate the runaway, what is the acceleration as a function of time in each interval? How about velocity? The latter must, of course, be continuous at t equals 0 and t equal big T. Assume that the particle was originally at rest, i.e. v at negative infinity is 0. Okay, that'll come back later for sure. And then part E, plot A of t and v of t, both for the uncharged particle and for the runaway particle. That way we can see the difference. For the uncharged and the charged, and for the runaway charged particle, non-runaway charged particle, subject to this force. Okay, well, we got ourselves a mess, don't we? All right, to start off with, in part A, the equation of motion needs to be rewritten. Okay, well, what we were given was A equals tau A dot plus F over m. But we need to write this in terms of velocities, that way, or at least their time derivatives, so we can integrate with respect to time. So A goes to dv dt, A dot goes to dA dt, and F over m is just a constant, so who cares? Here, if we integrate from t naught plus epsilon to t naught minus epsilon in all accounts, what we see is that the dv is evaluated from the dt with dv cancels, so we're just evaluating the velocity, and we see that we get v t naught plus epsilon minus v naught t naught minus epsilon. Similarly here, we get the same setup, except now we have to multiply by tau. The thing about this force here is that we can push it on through, but we use force average during this interval since that could be changing with time and we don't know what it is. But again, if it's constant or if it, is something other than, if it is variation with time, we can evaluate it. But for the sake of this, we're just going to use the average force since it looks like an averaging integral anyways. So long as it's not a delta function, we are left with, in a limit as epsilon goes to 0 with, well, if epsilon goes to 0, we have v t naught minus v of t naught is equal to tau of a t naught plus epsilon minus a t naught minus epsilon. And if we put epsilon equals 0 on that forced average term, that goes to 0. Left-hand side goes to 0. Now we have 0 to the left, and we can divide tau. But if that equals 0, then we see that a at t naught plus epsilon minus a of t naught minus epsilon, well, if that's equal to 0, they have to equal. Thus, a2 is continuous. Okay? So what we had to do is show that the difference of the accelerations equaled 0. And now we show that that was the continuity condition. So that's pretty cool. That was easy. Now we get the nasty part to deal with. So for for regions 1 and 3, for t equal less than 0 and t equal greater than big T, the force extra is 0. So our equation of motion gets moved out to this. And we can rearrange this as such, where we get, A's on one side, T's on the other, and, work our way through separation of variables and integrate across, and then integrate across. So that's how we get 1 over tau integral dt, and then integral dA over A. Clearly then we have t over tau plus some constant c is equal to ln A. We have to solve this thing for A, so take the exponent of both sides of the exponential, use the properties to split it up, and we see that when we do that, e to the c is just another constant, so we label it big A. Okay? So to keep from any discrepancies, I use big A e to the t over tau for region 1, and I use A3 is equal to c e to the t over tau. So again, just change up the constants, and then the middle region we'll use b. Fair enough. What we see here is that we still have to modify the equation, and when we do that, we again split up and simplify via separation of variables. All the a terms to one side, all the t terms to one side, integrate. You see we get the same idea here, except now instead of ln of a, we get ln of a minus f over m. So if we solve this thing, we get a minus f over m, and then that's equal to e to the t over tau plus c, which is equal to b to the b times e to the t over tau. So pushing it through, solving for a, we get f over m plus b over t divided by tau. Pretty easy there. Go back to diff EQ if we have a problem. Now, C, what we have to do is apply the continuity at both of the boundary times. Hence, at t equals 0 and t equal big T. So if we're looking at t equals 0, then we have to have the boundary of the acceleration region 1 and acceleration region 2. Okay, so we're going to have constant A and constant B. Plug in 0, we see that those exponentials go to 1, and we see that the relation is A is equal to F over M plus B. Okay, if that's the case, if we put in time t equal big T, and we have to use the region 2 and 3 now, they have to be continuous, so we can write C in terms of the F over M and B. Everything has everything has an e to the big T over T term, so divide over everything, and that's where we get the negative big T over tau. Okay, so if I'm putting it all together now, I have A of t for each region, t less than 0, t between 0 and big T, and then t greater than big T. And we substitute in A and C accordingly, so we have everything in terms of B. Okay, that's our one thing that we do not have enough information to solve yet. Here, though, what we see is that, since everything's already in terms of B, to eliminate the runaway region, or in part 3, we need B is equal to the negative, so we actually need that coefficient to equal 0. So B would equal negative of the Fm e to the negative big T over tau. But if we want to avoid the pre-acceleration region 1, we'd need B is equal to the negative F over M to make that coefficient 0. But clearly B cannot be simultaneously both. We have an exponential factor off. So we can only choose one. So if we choose to eliminate the runaway region, we see that region 3 goes to 0. But now we have B is equal to negative F over M, e to the negative T, big T over tau. So you see, we just, once we apply B, we can factor out an F over M for both of these things and, combine exponentials accordingly. Just be careful with the plus sign, minus sign, where they need to go. As you see, it's, that was a final condition needed for what B was. And so if we want to find the velocities now, we know that A is equal to dv dt, so kick over the dt term, separation of variables again, and integrate across for each region. Okay. D here is determined by the condition that v at negative infinity was 0, or it started at rest, essentially. So we just get rid of that. Now, similarly for region 2, we integrate across the acceleration at region 2. E is determined by the continuity of v at t, at v equal t equals 0, so set the two things equal to each other, and we see that E is equal to F tau over M. Since A is equal to 0, V is a constant, say G, and the constant is found via the continuity at T equal big T. Okay, so anytime we take the time derivative of a constant, it goes to 0. So set everything equal to each other at big T, let it cancel, or rather let it simplify through, and we see that the tau's cancel, so our actual constant is F over M times big T, which that kind of makes sense. Force times time gives us some kind of other unit than meter per second squared gives us a velocity, so that meters per second. That makes sense. So we combine everything in our results there. That will conclude the analytic part. Now we need to graph it, don't we? So if we go back, what we see here in this acceleration graph is horrendous, so let's walk through it slightly. For t less than 0, we see we have the pre-acceleration region, which has some thickness tau from the origin based on the constants that we have. Clearly, we decided to eliminate the runaway region, so everything stops at big T as far as acceleration. Clearly, if we just have an uncharged particle, there is no radiation reaction, so that's just a flat line that ends abruptly when we cut off the force at time t equals 0. But here you see we have this pre-acceleration region, which we could graph with the exponential. And then you see here that for any time between 0 to t, we have to gradually die off, and that's what the negative exponent tells us. So that's kind of weird. This pre-acceleration and runaway region are definitely something that need to be investigated because they are monstrous to this theory. And if we look again at the velocity, we know that after big T, it's just a constant. So we see a line here that just goes to constant. But that's equal to both the uncharged and the charged, so they meet up there. But you see that the charge has a velocity much greater than the uncharged, where the uncharged was just a linear line replicated by whatever the force was. So if the force was constant, then we see it just keeps, the velocity goes up at a constant rate, hence the acceleration being constant. But with the pre-acceleration region and it being a charged particle, we see it pre-accelerate up, concave up, and then it accelerates to a flat line at between 0 to big T, so concave down. Yeah, pretty unique stuff, and the papers attached will show even more than what I could describe. But be ready for this particular thing to pop its head up again.